All right, welcome you guys. We are going to talk about minerals today for our second lecture in this unit. So what are we going to talk about today? We are going to cover what minerals are. So I know a lot of people probably have heard of minerals, know a little bit about minerals, think why the heck do we have minerals in food and diets and why do we need them? So we'll talk about that, and then we'll cover our two big groups of minerals, macro minerals and micro minerals, also called trace minerals. So we'll go through that. I have them listed here, but we'll go through them individually as well. And then we'll talk a little bit about deficiencies and toxicities with some of these minerals. So what happens if you don't get enough, or what happens if you get too much. And so we see a little bit more in the toxicity level with minerals than maybe we do with vitamins. So what are minerals? So in contrast with vitamins, which are organic compounds, these guys are inorganic elements, and they can be classified as either micro or macro minerals. So what does macro and micro mean? It means that what is the relative amount present either in the animal and what is required in the diet. Okay, so macro usually means bigger, micro meaning smaller. So that is how we classify these two different groups of elements or minerals, as how much do we have in our body and then how much we require in the diet. Now, minerals are required as a nutrient in many species, so not all species require the same minerals, just depends on the species. And a lot of them are essential for metabolism, so we do utilize them in the body. Okay, so we'll talk a little bit about that. So first, let's talk about our macro minerals. So we're just going to go through them. We're not going to go through them in great detail just this minute, but we're just going to list them and say, you know, what they are. Okay, so the macro minerals we're going to talk about are calcium, phosphorus, magnesium, potassium, sodium, chlorine, and sulfur. Okay. So most of these guys are metals, okay? So chlorine is a gas, that's the only one that's a gas. And they are present in high amounts in the animal or in us as well. And they are required in relatively large amounts in the diet, so we can actually refer to them in a percent amount. So we need a percent amount in our diet. So these guys are the macro minerals, so we need quite a bit of them. And so you have their element at the bottom there. It gives you a little idea of what it looks like in their natural state, what their atomic number is, and all of that. So just, you don't need to memorize any of that, but just as a refresher for our elements and our and you know, going back to the periodic table, right? Way back when, right? So now what are the micro minerals that we'll talk about? We do call them trace minerals, so I may interchange those words, but trace or micro meaning small, right? So we'll talk about copper, zinc, iron, iodine, and manganese. So again, these guys are metals, okay? And these guys are present in low amounts in the animal, okay? So we only require a very small amount of them in our diet. So low that we talk about them in parts per million or milligrams per kilogram, okay? So ppm is parts per million, and that's probably the most common. We do see milligrams per kilogram as well. So where do we find these minerals? What are the sources of these minerals? So how we get them, or how animals get them as well, is in our diet, right? So in the different foods that we eat, especially diets that contain, bone products as well. So that's a big one for calcium and phosphorus. And then soil, right? So soil has minerals in it. And so depending on where the grass is grown for different hays, you can get an uptake of the mineral in the food, but also just the grazing animals that are out there eating the grass that's been growing in the dirt, and they're eating some of the dirt as well. So this can even be up to 10 to 25% of their intake in some of these grazing animals that do end up eating some of the soil. Water as well, right? So water has minerals in it, so it just depends on the water source and the different amounts of minerals that might be in that water, which could be good or bad. But mineral deposits, that's really the main source in the earth, right? So it's large quantities of minerals in the earth's crust, which is what is going to, then become in the soil, in the water, and things like that. Okay. Now we call ash, as we talked about how we break down our food and find out what percent of different nutrients we have in the food stuff, ash is what we consider to be the minerals. It has a very small nutritional importance, but it is the content that is, how we measure how much minerals we have in an overall feed, but we break that down further into, either percents for those macro minerals or the parts per million for the micro minerals. But the ash is kind of the overall content of minerals because it's the inorganic material, okay, in the feed. So let's talk a little more in depth about our macro minerals first. And we can kind of split the macro minerals into two main groups by their functions in our body. Okay, so what do they do in our body? So the first group is calcium, phosphorus, and magnesium. So these guys are structural components. Think the skeletal system. That's a big part of their function, but they do have other functions as well. So we'll talk about them in greater detail. Our second group is sodium, potassium, chlorine. So kind of think, electrolytes, right? So these guys have a lot of jobs in the cell function, acid-base balance. So we'll talk about them as well, okay? So first, let's talk about those macro minerals in the first group. So let's talk about calcium and phosphorus, and we'll talk about them together. So we find them in about 99% of calcium and phosphorus in our body lives in our bone and teeth. So that's where we physically find our calcium and phosphorus. And so then we can take from that source of calcium and phosphorus for other things as well, because calcium also controls the excitability of our muscles and nerves. So nerve impulses, muscle contraction, right? So all those things utilize calcium and the calcium ions, right? So we get those calcium ions from breaking them down from our bones. So the source in our body is the bones. Now, a big thing about calcium and phosphorus, especially together, is that we require a certain ratio of calcium to phosphorus in our body. Not only do we, need a certain amount of calcium and phosphorus, but we need a proper ratio. And the ideal ratio is 2 parts calcium to 1 part phosphorus. Okay, so on the right-hand side, they're equal, but that's not true, right? We should have 2 times the amount of calcium as phosphorus, but it just kind of shows you, how we compare calcium and phosphorus, okay? So let's talk a little bit about calcium in our blood, right? So we said we store the calcium in our bones, but how do we actually get it into our blood to utilize it for things like muscle contraction and nerve stimulation? And it has to do also with a little bit with vitamin D plays a big role in the calcium levels in our body. So say we have a decrease in our blood calcium. So that's going to stimulate some things that's going to happen in our body. And one of the biggest things it's going to release is a specific hormone called parathyroid hormone. And that's going to do a couple of different things. What it's going to activate is it's going to increase our absorption of calcium in the GI. And that's where vitamin D comes into play. So vitamin D helps, the active form of vitamin D in our body, helps that increase of calcium absorption in the GI tract. So we're going to get more calcium from the GI. We're also going to increase our bone resorption. So bone resorption means that we break down a little bit of the bone to release that calcium into the bloodstream. We're also going to increase our kidney reabsorption. So we're going to try to take more calcium back into the bloodstream from our kidneys instead of excreting it. So a bunch of things happen, but the overall process causes an increase in our blood calcium levels. So our calcium levels in our blood are very tightly regulated, meaning that we pay very close attention to how much calcium we have in our blood. And so with the help of this hormone and the whole endocrine system, we tightly regulate the amount of calcium in our bloodstream, okay? So here's just another image of kind of what happens with calcium and phosphorus in terms of kind of stimulating things and negative feedback, meaning if you have too much of something, it's going to stop the production or breakdown of other things. So just to kind of visualize what's going on if you have decreased calcium. What's going to happen with that parathyroid hormone. So it's going to stimulate the kidneys, the gut, and the bones, okay? But the overall idea is that we increase that calcium. Now, don't worry as much about what's going on with phosphorus. That can be a little bit confusing, okay? So don't worry too much about that. Sometimes they work in opposite. So now there are some problems if we don't see enough calcium, phosphorus, or vitamin D in our body. And that is termed metabolic bone disease. It's kind of the overarching disorder, but it can be due to a couple different problems. It's also referred to as rickets in growing animals or osteomalacia in adult animals or ourselves. Mostly we're talking about humans when we talk about rickets and osteomalacia. Metabolic bone disease is usually more referred to in our animals. And what are the symptoms that are associated with this disease? We see enlarged joints and or growth plates, just depending on the age of the animal, deformed long bones. So usually they can be bowed, as in that x-ray on the bottom right-hand side that we see in rickets. And we can also see fractures, okay? So what is it caused by? So usually it's caused by these three things, and one of the big ones is a deficiency in calcium in the diet, because then, or an improper balance of calcium to phosphorus, that can also cause it as well. Because what happens if you don't have enough calcium coming in? Well, you're going to take it from your bones, right? So that's going to cause these problems that we see in our bones, because you're going to leach out all that calcium from your bones. They're going to become soft, right? So you won't have that mineralization, that density of the bones. We can also see it in inadequate UVB or sunlight, UV radiation. Because the UV sunlight is what activates the vitamin D into the active form that helps increase the GI uptake of calcium. So that's a big one for husbandry, is inadequate UV light. We also see it in end-stage kidney disease. Okay, so if we think about back to what our ways of getting calcium are, and one of them is more resorption in the kidneys, reabsorption. And so if your kidneys aren't working properly, then you're just going to excrete all that calcium instead of reabsorbing it. So that can be a cause as well. Less common than the other two, but can be a problem as well. Now, another disorder that we see that is similar to metabolic bone disease, but due to a different cause, is called nutritional secondary hyperparathyroidism. So if you think of hyperparathyroidism, that means too much parathyroid hormone. So this is caused by too much phosphorus in a diet, and what happens is it throws off that calcium phosphorus ratio. So what ends up happening is that it actually depresses the calcium absorption in the GI tract. So it's going to cause an overall decrease in calcium, okay? And so what we now know that happens with a decrease in calcium is that our parathyroid hormone is going to increase, right? To try to increase that calcium level. So if we increase that parathyroid hormone, we're going to leach that calcium from the bone, which is then replaced by fibrous connective tissue. We do see this in horses and some other animals as well. It can also be referred to as big head syndrome because they lay down all of this fibrous connective tissue in their bones, which is kind of crazy to see, the symptomatic disease. So anyways, it's very similar, right? But a little bit different because it's due to phosphorus and not necessarily a decrease or calcium directly, okay? So another problem that we see with a low amount of calcium, and this is an acute hypocalcemia, meaning the calcium levels drop very quickly. And this is also called milk fever in cows. So in the dairy industry, they see this a lot and do a lot to try to prevent milk fever in their dairy cows. So it's an acute, meaning kind of a very fast and rapid drop in calcium, which can cause some major problems. So it causes convulsions, muscle tetany, meaning a rigidity, because you can no longer use that calcium for muscle contraction, nerve impulse. You can see that reflected in the symptoms. And what happens is we really just see it in dairy cows, and they call it milk fever because they have a huge drain of those calcium reserves when they start lactating. So they produce so much milk and so much of that calcium is going into their milk that they have this acute hypocalcemia in their body, which is quite crazy. So we do see this fairly common. Obviously, a lot of dairy practices try to prevent this from happening, and you can treat it as well if it does happen, but it is quite common if not prevented and treated. So a lot of us get calcium in our diet, right? So here are some things, some special things about calcium in the diet for certain species. So carnivores need bone or bone meal in their diet for that calcium because they can't synthesize vitamin D. So they need that high source of calcium in their diet. Herbivores get calcium in plant leaves. So plant leaves are a good source of calcium. And then lizards need to make vitamin D. They need a lot of UV light to make vitamin D to help them absorb calcium because they aren't good at absorbing calcium in their GI tract. So just some fun facts about calcium in the diet. So the disorders that we've been talking about are due to low amounts of calcium, but what happens if we have too much calcium? And that's called hypercalcemia instead of hypocalcemia. And it's also called calcium toxicity. So if you have too much calcium, what starts happening is that your soft tissues start to calcify. So instead of your bones being calcified, your soft tissues start calcifying, especially in areas of damage. So that's not good. But we also see urinary stones, calculi, they call them, in our urinary tract. So kidney stones, right, are a big one. And they can move down from the kidney through the ureters and into the bladder. We also see some zinc deficiency. Now, calcium, we'll talk a lot more about zinc, but calcium can reduce the absorption and utilization of other minerals. So if you have too much of it, it can block the absorption and utilization of some of these other guys, and specifically zinc. So we can see this zinc deficiency with hypercalcemia. So now our last macro mineral in our first group is magnesium. So we're not going to get into as much detail about magnesium, but just so you have a general idea of what it does work together with calcium and phosphorus for normal bone mineralization. So it is required for normal bone mineralization. But it also plays a role in regulating muscle contraction. So we said that calcium is required for muscle contraction as well. So magnesium plays more of a regulating role in that muscle contraction. So now what are some problems that we see with low levels of magnesium or hypomagnesemia? Grass tetany is another term for it. And what happens is you get this muscle tetany, okay, rigidity. So they go rigid. And we see this in certain areas where there's fast growing grass with very low levels of magnesium and maybe high levels of potassium. So potassium can antagonize magnesium, meaning it blocks magnesium, and so that therefore it kind of causes this deficiency. So not only do you have lower levels of magnesium, but you're also blocking magnesium as well, so that you get this overall significant deficiency in magnesium. And so they call it grass tetany because of these, areas of these fast-growing grasses. It can happen in those areas. So we see it in some cattle, okay? Now we can also see magnesium toxicity, so too high levels of magnesium. And this can happen in certain areas where there's high levels of them in the grass as well, in the hays. And they can cause stones in the GI tract, especially in horses, and we'll talk a little bit about that, or crystal formation in the digestive tract and urinary tracts. So we have this problem out here in California where our alfalfa, which is a hay, a food source for cattle and horses, and a lot of other animals, a lot of herbivores, that are high in magnesium. So we see these high levels of magnesium in our alfalfa and in the water. So the combination of the two causes this kind of magnesium toxicity idea. And what happens is they form these stones called enteroliths inside the GI tract. And so we see this in horses living in California that are specifically fed alfalfa. Very, very common, unfortunately. And so the only way to get those stones out is through surgery. So they actually have to open up their abdomen, open up their intestines, and physically remove these giant stones from their GI tract. So unfortunately, I've seen quite a few of these surgeries done. And it's a problem that we really only see out here in California. So it's kind of interesting. But, so that's the digestive tract. You can see these urinary stones or urinary crystals as well from high levels of magnesium. So now let's talk about our second big group of macro minerals, and that's going to be our electrolytes. Okay, so potassium, sodium, and chlorine. So these electrolytes are mandatory in very precise amounts and ratios for proper cell function, maintaining proper acid-base balance in all of our bodily fluids, right? So we talked a bit about, where our body water lives, right? So the majority in our cells, but also within the extracellular fluid as well around the cell too. So the majority inside the cell and then also outside the cell. But we also see it in plasma as well, right? So plasma in our blood is the majority of water. So we see these different electrolyte levels in those different bodily fluids. And it's very important to maintain the proper levels of them. Okay, so we'll talk a little bit more about that. But they're also needed for proper nerve impulse transmission, so especially sodium and also potassium. So when you have a nerve impulse, you have this depolarization of sodium. And so that's what actually stimulates that nerve impulse to go through the neuron. So it's just a little graph there to show you kind of this depolarization idea, but from a nerve impulse. So you don't need to, memorize any of that or any of the, percent of body weight and things like that for our body water, but just to kind of remind us where that that body water lives. Okay. So electrolyte ratios, so these ratios of these macrominerals in our body fluids are very tightly regulated, and they're also fairly constant across all species. So if you were to test, the body fluid of other animals compared to us, you would see the same ratios, okay? So we tightly regulate it, meaning that we pay close attention to it. So if we have any excess electrolytes, we're going to excrete them fairly readily in the kidneys. So we don't really hold on to any excess because that would throw off all of those ratios. So therefore, we really don't see toxicity as much with these macro minerals. The only one we can see having some problems is chronic high levels of sodium. And so what happens is this can cause hypertension or high blood pressure when we have chronic excess of sodium. It's essentially where sodium goes, water follows. So you get this kind of increase blood volume, and over time that can cause some hypertension. As you're moving more blood, your heart is working too hard. Okay. So again, this is just to kind of show you the different levels of those electrolytes in the different body fluid compartments and the different ratios of them. So just to give you an idea, but you don't, again, need to memorize any of this, okay? So we said that toxicities are fairly rare with these electrolytes, but we do see some deficiencies. And what can happen? So if we have a deficiency in potassium, potassium is very important for our normal electrical impulses in our heart and our heart muscles. So we do get this abnormal ECG or electrocardiogram if you have low levels of potassium. You can also die from significantly acute high doses of potassium as well. Potassium chloride can kill just about any animal. So potassium can be quite dangerous, but if you're just eating things with potassium in them, that's not going to cause a toxicity because your body will be able to get rid of the excess. You have to have an injection of potassium chloride to be able to cause that. But you also see muscle cramps and fatigue with low levels of potassium. So, we're all kind of familiar with, eating your bananas that have high levels of potassium to keep yourself from having those muscle cramps. Sodium chloride, right? So you definitely see this decreased growth rate with kind of deficiency in sodium chloride, but that's fairly rare because animals really have a strong desire for salt in their diet, as we can all attest to, right? We love our salty chips. But you can only really see it when water is restricted, okay? So again, sodium chloride deficiency is not too common, right? It can be if you excrete too much sodium, right? You're sweating too much, so you get a depletion of these electrolytes. And that's kind of where, your Gatorade and electrolyte waters come into play in that idea. But again, it's fairly hard to get too deficient in sodium and chloride. So our last macro mineral that we're going to talk about is sulfur. And sulfur is found in organic nutrients. So we do see it in some amino acids, some B vitamins. So again, we can get sulfur through some of these organic nutrients as well. Okay. It is important in metabolism, so we do need it for normal metabolism, but it's not as clinically significant as some of our other macro minerals. So a lot of people kind of forget about sulfur, but we do need sulfur in our body for normal metabolism. And those are just two examples of amino acids on the right-hand side that contain sulfur in them. And then we do have some foods that are high in sulfur as well. All right, so now let's cover our micro minerals, or those trace minerals. And so they're micro about the amount. So they're small amounts. We don't need them as much in the diet. But we do need them. So how we measure trace minerals is you'll see it a couple different ways. So 1 part per million, so that's ppm, is the same thing as 0.0001% or 1 milligram per kilogram. So those are all equal in the amounts. And so the thing about micro minerals is that it's varying depending on where feed is grown. So this is very important when you're talking about, hay and things like that, grasses and hays that are grown in different parts of the country because of the soil levels of those minerals. So the plants take up the minerals from the soil when they're being grown. And so it can depend on where they're grown, and some areas have higher levels than others. It's more important, I think, in a deficiency standpoint, where you're talking about if a feed is deficient in a mineral. It's usually due to where it was grown. So the overall function of our microminerals that we care about is they're usually activators of enzymes, enzyme systems, or even components of organic compounds. So we utilize them as these activators or just part of these other important compounds, okay? So our first trace mineral we'll talk about is copper, and copper is needed in relatively small amounts, even in the trace mineral world, and that's 5 parts per million. And copper is really needed for iron metabolism, so they work kind of together. Connective tissue, bone formation, and nervous system function. So a lot of these connections, structural formation, as well as the nervous system. But another big thing, and this is where it can come out in a deficiency, is it's also needed for melanin production, which is the pigmentation in our hair, the wool of animals, and even the skin. So sometimes you see this problem in the pigmentation of hair and wool if you have a deficiency. So let's talk a little bit about deficiencies and toxicities with copper. So copper, you may not get like a true deficiency in terms of not enough of copper, but it can get bound up easily with other minerals and compounds, meaning it'll kind of bind it up and make it useless, right? So you can't use it in the places where you need it. So that it will give you like a relative deficiency essentially. So what do we see with these deficiencies? We talked about a big one with the melanin formation. So we have, this kind of depigmentation or discoloration of hair and wool. And it also causes this kind of twisting or kinking of the hair and wool. So you have this kind of odd, thing that comes out in the hair. So there's an example here on the bottom right hand side where you see that there's a normal diet, so you have normal pigmentation in the wool, and then you have excess molybdenum, which is another metal, and it can actually get bound up. It binds up copper, so essentially it gives you this relative deficiency, and then you add copper back in and kind of the pigmentation comes back. But we also said it's important for structural components with our connective tissue. So the fibers in the connective tissue, collagen fibers, elastin fibers, can be defective as well. So we can see that. You also see anemia, so low red blood cell count. And this kind of neonatal ataxia, ataxia is a problem with their walking or motor skills. So they have this kind of sway back look to them. So, and it's in neonates, so newborns, that we can see this because we said that it's important for normal nervous system function as well. We can also see oxidative damage as well, and that's fairly common kind of across the board. We do see toxicity, mostly in ruminants because they are more sensitive, and you can see either an acute toxicity, meaning they had a high dose all at once, or you can see kind of a chronic toxicity, meaning they have kind of a higher amount over a longer period of time. And usually you see liver damage, maybe kidney damage or disease with copper toxicity. So our second trace mineral is zinc. So it is the second most abundant trace mineral or trace element, iron being the first. So we'll talk about iron next. And zinc is needed for kind of normal cell growth and division. So normal growth. So you might think of something that if we are deficient in, you might see growth problems. It's also really important in wound healing. So that's an important thing as well. Normal immune function, activation of the immune system. And a lot of people take zinc when they have a cold, right? So a lot of these lozenges and things like that that are kind of remedies or homeopathic remedies for being sick, a lot of them have zinc in them because it can help activate that immune system. But we also need it for carbohydrate breakdown. So kind of all this, catalytic, structural, regulatory function in the body and in the carbohydrate breakdown process. So now let's talk about zinc deficiency and toxicity. So again, it may not necessarily be a deficiency in the true amount of zinc. There are things that can block zinc, and high levels of calcium is one of them. And we kind of talked about that when we were talking about calcium. So calcium can inhibit zinc, which will cause, again, kind of this relative deficiency in zinc. So we said it's really important for cell growth. So if you have a deficiency, you see growth retardation, anorexia, weight loss. And we said it's really important for wound healing. So you get this drastic delay in wound healing. And another kind of outward symptom is this thickening of the epidermis, as shown in the picture, parakeratosis, which is these kind of areas on the skin that are thickened and look irritated. And so that can be a classic sign of zinc deficiency. And we really don't see too much zinc toxicity because it is fairly safe. There is this kind of wide margin of safety for zinc. So high levels aren't necessarily bad. But we do see a specific problem in some small animals if they were to ingest some coins, because a lot of coins have high levels of zinc in them. And then you can get this kind of anemia caused by this zinc toxicity from the coins. So now let's talk about iron, which is our most abundant trace mineral found in the body. And it's needed to make hemoglobin and myoglobin. So if you think back to kind of your biology, anatomy, hemoglobin and myoglobin are the molecules in our red blood cells and our muscles, respectively, that bind and carry oxygen and carbon dioxide through our blood cells and through our blood and in our muscles. And we store iron in the liver and the spleen. So that's where we store iron, and we can get a buildup of iron. We don't necessarily excrete or get rid of iron. So iron can slowly build up in the liver, especially over time. So we do see some toxicity with iron. So we do see iron deficiency, and what happens is we get this iron deficiency anemia. So anemia is just a general term for a low red blood cell count, and that can be caused by multiple different reasons, but one specific reason is iron deficiency. And it can be the most common type of anemia, and we call it microcytic hypochromic anemia, meaning that the cells are small, microcytic, hypochromic, meaning they don't have the red color, because hemoglobin is what gives red blood cells their color. And so they are less red or pink in colors. That's hypochromic. So you can see on the slide a normal blood smear on the right and a iron deficiency anemia, that microcytic hypochromic anemia on the left. So fairly classic type of anemia that we see with iron deficiency. So since we can store iron in our liver mostly, but also spleen and somewhat in the cells as well, we can see this iron toxicity, and we call it iron overload. And what happens is if there is free iron in the body, it can cause oxidative damage to our tissues. So we actually have these scavengers that go around the body and pick up the iron, the free iron, and brings it to the tissues. So brings it to the cells, brings it to the liver for storage so that it's no longer free and causing damage. So there are some causes though of this iron overload, too much iron. So hereditary, you can get it from a hereditary or genetic reason. But what we kind of care about is high iron in the diet, right? So it could be nutritional. And any sort of infection or inflammation can increase the storage of iron. So they pick up more of it and store more of it in the liver. And we store liver or iron as ferritin in the liver, and then we store it as hemosiderin in cells. It's kind of a secondary storage in the cells. Okay. And we said that the body really doesn't get rid of iron, so we only kind of collect it. Okay. So that's why we're so susceptible to iron toxicity. And there's a couple terms. Hemosiderosis is just too much iron. But then we have hemochromatosis, which is true cell toxicity from too much iron in the cell. So, you know, we do see this in certain animals that maybe have too much iron in their diet or anything like that. So we can see iron overload. So what does iron overload look like, right? So since we have too much in the liver, what does it actually look like? And you can have an acute toxicity, meaning you have a really high dose all at once, which is fairly rare. Chronic toxicity is much more common, where you get kind of an increase over time because you're just storing more and more of it. So if you have an acute toxicity, you have kind of classic symptoms, right? So vomiting, shock, metabolic acidosis, and death. It's a fairly common kind of acute reaction to a toxicity. And then chronic, you see diarrhea, reduced growth. Also, you don't get as much efficiency in their feed, so they can't utilize their feed as well. So that's where they get kind of a weight loss, reduced growth. And since you have too much of it, you get a lot of this free iron and free radical formation causing damage, right? And since it all's going to the liver, you get liver toxicity. So with that and chronic liver toxicity, you get fibrosis and cirrhosis of the liver, which is kind of classic, liver damage problems, right? So there are some treatments for iron overload, and that's a phlebotomy, where you actually take out the red blood cells. So you actually let blood out, bloodletting, to try to decrease the amount of iron in the blood. You can also bind up the free iron via chelation therapy. So you use another compound that binds iron, and then you're able to excrete it because it can excrete that compound that bound the iron. And we'll talk a little bit more about that. So here's just an image to better kind of understand chelation therapy. So you introduce an iron chelator, meaning a compound that's going to bind iron, any sort of unwanted heavy metal, such as iron, and it essentially causes iron to be chemically inert so that it can no longer do damage, it can no longer be stored, and thus it allows that iron to kind of either be excreted or pass through the body without further harming the tissues. So another trace mineral we'll talk about is iodine. So iodine is very important as well, but we really only need a very small amount, and we actually call it ultra trace mineral because it's less than 1 part per million. So that is very small amount. And we need it to make thyroid hormone, or T3 and T4, in the thyroid gland. So thyroid hormone helps with basal metabolism, kind of your resting metabolic rate. And so if you have too much thyroid hormone, you kind of have higher metabolism. Too little thyroid hormone, and you get hypothyroid or low metabolism and weight gain, which can be a common problem these days in older women. But we do see hyper and hypothyroid in animals as well. So we do add it to our diet. So there are foods that are rich in iodine, but we do see this iodized salt. Iodine is not very stable, so you can add it into salt, and that's one way to get it into the diet. So what do we see with iodine deficiency? So there's kind of a classic symptom of iodine deficiency, and that's a goiter, which is an enlarged thyroid gland. So what happens if you don't have enough iodine, your body can't produce enough thyroid hormone. So essentially your body thinks you're low in the thyroid hormone, and you start stimulating the thyroid gland with thyroid stimulating hormone to say, hey, thyroid, we need more thyroid hormone, start producing it. So it starts to enlarge and engorge, trying to make more thyroid hormone, but it can't because it doesn't have enough iodine. So there are some causes of this. There are some plants that contain these thioglycides, they call them, and they're goitergenic, meaning that they actually cause an iodine deficiency. And whether that's binding iodine or blocking the function of it, I'm not quite sure. But we do see this in some of our cruciferous plants. Okay. Soils can also be iodine deficient. So plants that are grown in soils that are iodine deficient. You do see this in kind of third world countries as well, where they don't get enough iodine in their nutrition. So they don't eat enough iodine containing foods. We can see iodine toxicity, but it's a little more rare, and it, interestingly enough, also causes goiters. So if you see a goiter, it may not necessarily be a deficiency, it could be a toxicity, but more often than not, it's a deficiency. So here's just a little depiction of what happens if you have low thyroid hormone. It's going to tell your brain that it needs more thyroid. So the brain releases, the hypothalamus specifically releases more of that thyroid stimulating hormone to say, hey, thyroid gland, produce more thyroid. But we don't get an increase in that thyroid hormone to feed back and tell the gland to stop producing it. So usually you get this normal feedback system where you have enough T3, T4, and it'll shut down the production of thyroid stimulating hormone. But if you're just not producing it, then it's going to keep stimulating it and create these goiters. So here's just a world map kind of showing what parts of the world have some iodine deficiency in the soil, or maybe even excess iodine. So just kind of an interesting thought. And these are areas where you can see this goiter development, either from a deficiency or toxicity. So another trace mineral that we see in kind of low amounts is manganese, but it is interestingly enough required in higher amounts in reproductive animals and more specifically poultry. So specifically poultry need quite high levels of manganese. So they need 50 parts per million. Reproductive animals need 40 parts per million, whereas the normal amount that's required is only 1 part per million. So that's quite a big difference. And manganese is needed for proper bone formation. It's similar to magnesium in its function, and it can actually replace magnesium in many reactions. So even though it's a different compound, it's a different element, right? Manganese, it sounds very similar to magnesium. So that's a good way to remember its function. So we do see manganese deficiency, especially in poultry and reproductive animals. So you can obviously get some reproductive problems and this kind of decreased bone growth, decreased bone formation problems. And there's a very specific symptom that we see in chicks called porosis, or a slipped tendon, in these chicks and these birds that are trying to develop, and they have these really enlarged hock joints. So if you can see, their hock joints are really enlarged and they can't bend them properly. They have these slipped tendons, so that joint, that hock joint, doesn't function correctly. So this is a classic sign of manganese toxicity in birds. Deficiency. Toxicity is rare. That's the thing. So toxicity is fairly rare. It has a wide margin of safety. I mean, if you can, 1 part per million to 50 parts per million. So we really don't see manganese toxicity, but we do see this deficiency in reproductive animals and poultry. So now we'll talk about a few other trace minerals, selenium being an important one because it actually was first discovered as a toxic mineral. So they thought at first that it was toxic, but it's really only because it has a very narrow safety margin, meaning that we require a certain amount, but only less than 4 parts per million. If you get a dose that's higher than that, such as 5 parts per million, it can become toxic. So selenium does have some important roles. It plays a big role in cell membrane integrity, but they also discovered that it helps to prevent or even reverse symptoms of vitamin E deficiency. So we talked about vitamin E deficiency in our last lecture, which can cause that nutritional muscular dystrophy and encephalomalacia. So some muscular problems, white muscle disease, as well as these brain abnormalities as well. So we do see a deficiency here in California and across the state. There are certain areas that have selenium deficient soil. So hays and grasses that are grown in those areas, we see this selenium deficiency. And a deficiency can cause some problems as well. So some liver necrosis, cardiomyopathy is a big one, which can then lead to congestive heart failure. You also see muscular dystrophy as well. So it kind of goes back to that, kind of similar to vitamin E deficiency. Okay. So this is just kind of a map of the selenium levels in the soil. So we're kind of in a variable area, but specifically Southern California is known to be somewhat low in selenium. So you see that, you know, in the Midwest, they're quite good, and then kind of the East and the West has some low levels of selenium. So we said that selenium can be quite toxic. So we said we require less than 4 parts per million, but if you get 5 parts per million or higher, it's toxic. And acute selenium toxicity can happen and was seen quite tragically a number of years ago in horses. There was a string of polo horses in Florida that received the wrong dose of selenium. So selenium injections have become more popular for sporting events such as polo horses, these athletes, and the pharmacy got the dose wrong, and the entire string of polo horses died from this acute selenium toxicity. It was all over the news and it was very sad. But you get this kind of blind staggers, they call it. They get abnormal movement, pulmonary edema, so they get fluid in their lungs, diarrhea, and then death. So they all ended up dying, which was very sad. And it was kind of a learning curve for everyone about how toxic selenium can be. So more often you see kind of a chronic selenium toxicity. You can see liver disease, kidney disease, kind of this emaciation or weight loss, sore feet, cracked hooves, lameness problems. So you can see some chronic selenium toxicity. So our last trace mineral we'll talk about is cobalt, and cobalt is really only needed in ruminants. So they require cobalt to produce vitamin B12. So any sort of deficiency in cobalt will mean a deficiency in vitamin B12. And with that, you get anemia as the main symptom, so that decrease in red blood cells. We can see a toxicity in cobalt. If you get too much cobalt, you get this mild polycythemia, which is an increase in our red blood cells. So deficiency causes low red blood cells, toxicity causes too many red blood cells, and that can make the blood thick, and so it doesn't flow through the vessels as easily, and you can have some symptomatic problems with polycythemia. But this causes just a mild polycythemia, so there aren't probably too many side effects from it. So that's it for our minerals this week. So we've covered vitamins and minerals, and we will talk about some toxic minerals as well as some toxic plants next week. And they're not going to be the classic plants that kind of everybody knows about, you know, your house plants for cats and dogs. I'm going to talk a little bit more about kind of out in nature and maybe enclosures that some of our either exotic animals or large animals might be exposed to. Okay, till next time. Thanks again.